Hi, I'm Adila Maizan binti Muhammad Zokhairi from group number 6. I will presenting theoretical part and results obtained for task number 1, which is classification part. Convolutional neural network CNN for classification. So convolutional neural networks are deep artificial neural networks. We use CNN to classify images, cluster them by similarity, and perform object recognition within scenes. It also extracts relevant features from the input images and maps to the corresponding classes, which enabling accurate image classification. So how CNN use image classification? Image classification involve assigning labels or classes to input images. It is a supervised learning task where a model is trained on labeled image data to predict the class of the unseen images. Below shows the different layers involved in the image classification. So for the first layer is the input layer. Basically, the input layer of CNN takes in the raw image data as input. The images are typically represented as matrices of pixel values. The dimension of the input layers also correspond to the size of the input images. And then the second one is the convolutional layers. Convolutional layers are responsible for features extraction. They consist of filters, which also known as kernels, that are convolved with the input image to capture relevant patterns and also features. So this layer learns to detect edges, textures, shapes, and other important visual elements. So the third layer is the pooling layer. Basically, the pooling layer reduce the spatial dimension of the feature maps that was produced by the convolutional layers. They perform downsampling operation, for example max pooling, to retain the most salient information while discarding unnecessary details. So this actually can help in achieving translation invariance and also can reduce the computational complexity. The next layer is the fully connected layers. So fully connected layers is the output of the last pooling layer that being flattened and connected to one or more fully connected layers. These layers function to classify the extracted feature. And then the fully connected layers also learn complex relationship between features and output class probabilities or prediction. The last layer is the output layer. So the output layer represents the final layer of the CNN. It is also consists of neurons that are equal to the number of distinct classes in the classification task. So the output layers provide each class's classification predictions that indicate the likelihood of the input image belonging to any particular class. So next, how to use CNN for classification. First, we can define the architecture of the CNN. Second, we do the pre-process the input images. Third, we train the model on the labeled data. For example, on this task 1, which is PETCAN. And then number 4 is we can access its performance on the test images. So how to complete the task? For task number 1, we use the Google Colab for model 1 and model 2. However, in the model 2, we use pre-trained model, which is VGG16 architecture. So what is VGG16? VGG16 is the model consists of 16 layers that consists 13 convolutional layers and 3 fully connected layers. Basically, each convolutional layer has 3 times 3 filter size with 1 pixel strides. So how to use the VGG16? First, we can download the weight and load into our own model. These steps are being shown in the demo video, and then we use the model to classify images or extract features from them, and then we can use to train our VGG model, where we use the dataset of the label images, and then we train the model using a deep learning framework such as a TensorFlow that being used in this project. Next, the results for model number 1. So basically, these two graphs here shows the training and validation accuracy and training and validation loss of a machine learning model over epochs. So for this project, we use 100 epochs. So for the graph on the left side is the training and validation accuracy. So the left graph shows the training accuracy and validation accuracy over 100 epochs. Basically, both training and validation accuracy fluctuate over time. We can see from the graph, and the training accuracy starts just above 0.5 and then quickly increases, which is reaching around 0.7 with some fluctuations happen. And then the validation accuracy also starts around 0.5, but it doesn't show a clear increasing trend as the training accuracy does. So it fluctuates around 0.7 marks, but it generally remains below the training accuracy. So this graph is said to be overfitting as the training accuracy is higher than the validation accuracy. On the right side is the training and validation loss graph. So the right graph shows the training loss and validation loss for the same number of epoch as the accuracy. So the graph can be overfitting as the validation loss we can see it's quite volatile if we compare to the training loss. This is because the validation loss does not decrease as steadily as the training loss. Model 2 result is based on the training we use pre-trained CNN model, which is VGG16. So the accuracy graph on the left side shows an increasing trend for both training and validation data sets, which by means that the model is improving its prediction. However, since the validation accuracy is consistently lower than the training accuracy, it will indicate that the model is overfitting the training data and not performing well on the new data. And then on the right side is the loss curves that shows a decreasing trend for both training and validation dataset. This means that the model is learning from the data and then it reducing the error. However, the validation loss is constantly higher than the training loss, which suggests that the model is overfitting the training data and not generalizing well to the new data. Next is the comparison between the Model 1 and Model 2. For Model 1, the accuracy graph shows a smaller gap between the training and validation accuracy. The accuracy graph also shows increasing trend as training accuracy does, but generally it remains below the training accuracy. For model number 2, the loss graph shows a smaller gap between training and validation loss. So the loss graph shows more expected behavior with the validation loss decrease over time. So the conclusion that we can be made is that Model 1 has a better stability in terms of the validation metrics, but Model 2 shows better in terms of the generalization and stability of the training and validation loss. That's all. Thank you.
Greetings to our doctor, Dr. Razali. My name is Evina Maria and my metric number is CE200108, and today I'll be presenting the video demonstration for our task 1 where we will be using the Google Colab to run our Python code. So as you can see, for the first line of coding is that to mount our Google Drive account to the Google Colab, and then we declare the directory files for the files that we'll be using for our images to train. And the third coding is to calculate the training and the validation length for the image classes. So as you can see here, there are 3 classes, which is the can, pet, and tetrapet. And once the coding is run, the result will be shown for the train length and validation length for the 3 image classes. And next is this is the coding where we will create our own model, and here is the result where it is classified by the layers, output shape, and the parameter. below here shows the total parameter. As you can see, is 917921, and the non-trainable parameter is 0, while the trainable parameter is 917921, same as the total parameter. And the next is, this is basically to classify the images to the classes. So once we run the coding, the output shows that it has been found that there are 1811 images belong to 3 classes, and it also displays the data batch shape and the labels batch shape. So this is basically the training, where we have set the epoch to 100 and step per epoch is 47, while the validation step is 21. So once the trainer counts completely until 100, we will then able to plot the graph for both training and validation accuracy. So as you can see here from the graph, it shows that the loss curve actually decreased for both the training and the validation data set. That means that the model is learning from the data and reducing the error. But it also can be seen that the validation loss is a little bit more higher than the training loss, which means that the model is overfitting the training data and it's not generalizing well to the new data. And as for the accuracy curve, also shows an increasing trend for both the training and validation data set. That means that the model is improving in terms of its prediction. Even though the validation accuracy is a little lower than the training accuracy, that means it also indicate that the model is overfitting again with the data, training data, and it's not performing well with the new data. So the gap between the training and validation curve is quite large and stable. That means the model have a high variance and a low bias. Also, that means that the model is sensitive to noise and variability in the training data, and did not capture the underlying patterns and relationship to the data. So for my suggestion, after running this model, it can be improved if we use different model architecture or hyperparameter to optimize the learning process, such as like changing the number of layers, the neurons, or the learning rate. That's all for me. Thank you.
So for the code number 2, which is from Google.Colab import drive, so basically this code is used to access the Google Drive files directly from our Colab notebook, and then we can work with other files that were stored in the Google Drive. As for the code number 3, which is import OS, we use this code to change the directory to another file that name task inside the Google Drive. Next, for the code number 4, which is train_dir, this code is actually shows that the variable will store the path to the general training directory under the train files, and then can train dir and also pet train dir. So basically this shows that the variable is store the path to a specific subdirectory for training with the label name pet or can, and then it is also a subdirectory under the train file. And then the name here shows that it will contain the images that related to either can or pet. And then moving to the next code, which is tetra_pet_train dir. So this shows that the variable stores the path to another subdirectory for training with a label name tetrapack, and then it is also a subdirectory under the train. So next one, the code will indicate the print can train length, print pet train length, print tetra train length. So basically the code will indicate the process of printing the length of the list of the files in the pad, can, and also tetra train lang training directory. So here, after we run the code number 4, it shows all the related informations, which is the can train lang, pad train lang, and also the tetra train lang. Also with the cat val lang, pad val lang, and also tetra train lang. Moving to the next code, which is code number 5, it shows that the import TensorFlow SDF, which by means we will import the TensorFlow library, and then move from TensorFlow.keras optimizer import RMS prop. So which by means we will import the RMS prop optimizer from the TensorFlow.keras optimizer module, and then this optimizer are used during the training of the neural networks, which is to minimize the loss function. And then from TensorFlow.keras.processing image import image data generator. So this code is used to import the image data generator class from the TensorFlow.keras.processing image module. And then the image data generator is used for the real-time data argumentation during the training of the neural network of image data. And then next, the code from Keras application import VGG16. Since our project uses VGG16 for the task number 2, so we will import the VGG16 model from the Keras application model. So for the code number 6, we will show the code to creating VGG16 convolutional base using TensorFlow and also Keras. So from the code, which is code conv_base equal to tf.kerasapplication.vgg16, and weight image net include top files include shape 150, 150, and 3. So basically, we will create the instance of the VGG model where the parameter are passed for the image that we are expected to have the dimension of 150 times 150 pixels with the 3 channels. The last code, which is conv_base_summary. So here we will print the summary of the VGG model, which is include the layers name, output shape, and also the trainable parameter. So after we run the code number 6, we can see here the downloading data from the files. So it shows the layer type, output stage, and also the parameter. And then the last one, it shows the total parameter, the trainable parameter, and also the non-trainable parameter. Moving to the code number 7. So basically, all this code is to compile a neural network work, and then we setting the optimizer, the loss function, and also the metric that will be used for training. After the compilation, it will print a summary of the model architecture for inspection as stated in the code model.summary, and then it will show the total parameters, the trainable parameters, and also the non-trainable parameters. Next, moving to the code number 8. So basically, the code number 8 will has 3 methods, which is flow from directory, and also flow from data frame, which is stated in the code. And then train_dir, this is the code for the target directory, and then target size 150, 150. This is the code for all images will be resized to 150 times 150. And then since we use the binary cross-tropy loss, we need the binary labels, which by means we will indicate the code class_model equal to binary. Next, same goes to the validation process. We will evaluate the performance of the model on the validation dataset, which and also the image for validation will be resized to 150 times 150 as stated in the code here. And then for code for data_batch label_batch in train generator. So basically, this data will be print the shape of the current batch of the data. So when we run this code number 8, we can see that the result shows that it found 1011 images that belongs to the 3 classes, and then we also found 698 image belong to the 3 classes, and the data batch shape, also the label batch shape. Then moving to the next code, which is history equal to model.fit train generator, step per epoch is 10, epoch 100, validation underscore data equal to validation generator, and also validation underscore steps equal to 21. So basically this code, we will do the training for process that we run for 100 epochs, which is each of the epoch consists of 10 steps for training and also 21 steps for validation. So when we run the code for the, number 9, so it shows that it run the training for 100 epoch with the 10 step and also the training 21 step for validation. Moving to the last code, which is import matplotlib.pyplot splt. So basically all this code will tell us to create plots which we can visualize how the model's accuracy, that will be titled as training and validation accuracy, and also the models for the loss, which will be titled as training and validation loss. So this plot will shows the accuracy and loss that change over the training epoch, and then from the graph we can identify either the graph is overfitting or underfitting. So for the first graph here is the training and validation accuracy. So basically we can see that the dot on the graph shows the training accuracy, and then the signal here shows the validation accuracy. And next, the graph shows the training and validation loss. For the dot on the graph shows the training loss happen, and then for the single line on the graph shows the validation loss that happened during the validation and also training process.
Hi, good morning. I'm Losini from Group 1, and today I'm going to present to you about our assignment task 2. So this is our problem statement, which the specific problem is the hand revolve around the parking space management, particularly the lack of efficient and automated system to monitor the number of cars entering to UTHM premises. And the absence of such a system poses challenges in understanding parking occupancy, leading to the potential inefficiency in space utilization. Next is the solution that we propose. So because of the problem that I mentioned just now, we are proposing a custom YOLO module which will detect the car that entering the campus, offering real-time insights into parking occupancy. The goal is to create an automated system that not only informs administrator about the available parking, but also contributed to a more organized and sustainable campus environment through the use of computer vision technology. The next one will be the method. This is a simple overview of our method. So at first we have to set up our Google Colab with Google Drive, and then next we have to set up our YOLO framework, testing the pre-trained model on our image and video, download the image using simple image download, annotating custom dataset using RoboFlow, training our YOLO model on custom dataset, and test our YOLO model on image and video. This is the result which we test the custom YOLO on image, and this is how it look like when it is in video. So as you can see in the video, it is detecting the car now. So the next one is our Google Colab. This is how our Google Colab look like. As mentioned just now, first we have to connect to our Google Drive, and then next is setting up the YOLO framework. To setting up our YOLO framework, you have to enter the folder directory first, and then download YOLO v7 repository and install all the requirements required. Next, we have to copy the web of YOLO v7, download the dataset, and store in Google Drive folder. Next, we train our YOLO on custom dataset with 100 epoch. And finally, we test our custom YOLO module on image and video. And the result is as shown as just now. Thank you.